Welcome everyone to Practical Astronomy for October. Hope everyone is doing well. I just need to let you know this is being pre-recorded. We had issue with Steve not being available to run this as a live stream. So I've recorded it before the meeting, and to handle questions at the end, what we'll do is just use the chat as normal, but I will have to answer via the chat as well. So sorry about that, and just to let you know that next week the astrophotography group will be running a talk on the Monday night. We will have Introduction to Astronomy on the first Monday of November, and then on the second Monday we're going to run the Burbage lecture. Because we were unable to run the Burbage dinner this year with the lockdowns, we have arranged a special guest speaker from the UK, Dr. Karen Wakeford, and she will be presenting the Burbage lecture online. And straight after that lecture, we will be announcing the winners of the New Zealand astrophotography competition for the Harry Williams Trophy. So that will be interesting to see. I'm sure there'll be a lot of people out there eager to find out how they did. And yeah, well, we'll see you in that talk, and it should be a really good talk on exoplanet atmospheres. It's quite amazing that it's now got to the point where it's possible to find out information about the atmospheres of exoplanets, not simply that they exist and their orbital periods and mass and things like that. So it's quite an amazing uh, forward step in astronomical technology, I guess you could say. So, really looking forward to that talk. So, tonight we're going to be talking about telescope mounts, and hopefully, this talk will sort of resolve some questions people might have. There's essentially two types. There's the altitude azimuth mount and the equatorial mount. The alt-azimuth or alt-az mount, it basically has two axes of rotation. So you'll have one rotation that goes in altitude, which is just pointing up and down in the sky, angle of rotation from the horizon to the zenith, going from 0 to 90 degrees. And the other axis is called the azimuth axis, which is just the compass bearing that runs from 0 to 360 degrees. So 0 degrees is north by convention, and then 360 degrees is back to north, so you've done a complete rotation in that axis. The equatorial mount also has got two axes. The declination axis is basically rotating through the angle north and south of the celestial equator. So if you're pointing north of the celestial equator, you've got a positive angle. If you're pointing south of the equator, it's negative. So objects like, say, 47 Tucanae is about declination minus 72. That's directly translates to the equatorial declination axis. The other axis is called the right ascension axis, or sometimes referred to as the hour angle. So this is the angular rotation westwards from your local meridian. Now the meridian is the line that runs across the zenith, and it's the true geographic north-south line. So if you were to got a star to the west of the meridian, your local meridian, then the position is measured in units of time by convention. And if, for example, it had a hour angle of 1 hour, it would mean that it's 1 hour apart since it passed the meridian, so it's moved over to the western side of the sky. If it's 1 hour to the east of the meridian, then it would be 23 hours in this convention. But there are some software that I've noticed give this number between -12 and +12. So in this case, the positive hours are objects over to the west, and the negative hours to the east. So if your star had an hour angle of -2 hours, then it means it's 2 hours before it's going to cross the meridian. So for the telescope mount to work like this, it means basically that the right ascension axis has to point at the pole, in our case the south celestial pole, and the north celestial pole if you're in the northern hemisphere. So we're going to look first at various kinds of our alt-azimuth mounts, and the simplest one that'll be familiar to most amateurs is the Dobsonian mount. This is a design popularised by the late John Dobson, otherwise known as the sidewalk astronomer of San Francisco, and he got that name because he used to take his telescope out to city streets in San Francisco and get people to look at the moon and planets, and which is still possible under light pollution skies. Those objects are bright enough to see even from central city areas, and so he was a great popularizer of astronomy in general, but he also had his name associated with a type of mount called the Dobsonian mount, which is a really easy to make type of mount. And there was a big movement for making your own telescope back in those days because commercial telescopes were really expensive, even compared to prices today. So it was really worthwhile and to make your own, and so anybody could basically have a telescope. So this is the modern version of the Dobsonian, I guess you could say. You notice the telescope sits on a what you could call a rocker box, and the rocker box sits on two discs, and between the two discs at the bottom there's a bearing which allows the telescope and the rocker box part of the mount to rotate in azimuth. So normally the bearing will have an adjustment, and these ones is actually a knob in the middle which you can't see here between the two side pieces of the rocker box at the bottom, where you can tighten or loosen the pressure on the bearing. And the idea is you adjust that so there's a bit of resistance to the mount being turned, but it offers enough resistance so that it just won't be easily knocked off target. And similarly, the other bearing, which you can see if I bring the mouse pointer in, this bearing here sits in a recess in the rocker box, and there'll be a lining there, I think usually of formica or something with a really smooth surface to for it to move on. But you have an adjustment there which applies tension to the bearing, and again you adjust that to have it tight enough so that it will hold the telescope with its eyepieces without moving too easily, but not so tight you can't move it when you want to move it to a different object. So that's basically the way they work. You move the telescope up and down, you spin it around to position it anywhere in the sky. A completely manual telescope, and it's intended for visual use, or it is possible, however, to take short exposure photographs. I've seen some quite good lunar pictures done on these, and even some planetary pictures of Saturn and Jupiter. So you can get a more sophisticated version of this kind of mount. Basically what's happened here, it's fitted with a motor on each axis. So there is a motor on the altitude axis here, and there'll be another motor fitted on the azimuth axis, and you've got a little computerized control box that allows you to set up initial alignment so the computer can work out where the telescope is pointing, and it allows you to go to any position of the sky, and quite convenient for finding objects. Although I'm still a proponent of learning how to find objects visually just using a simple mount because it's a great way to learn the sky. Um, but yeah, this is certainly a big time saver, especially when you're getting started. This is another kind of Dobsonian mount, getting up to a very large size. This particular one is a company named Accession make these, and you notice that the altitude bearing is actually down here quite low down. The reason they can do that is because the mirror cell with a very large mirror is quite heavy, so basically the centre of mass is fairly low down with this telescope. And again, you'll spin the telescope around in azimuth, and again the telescope has got these truss poles which allows it to be packed down into a car for transport. And this particular one, to move it around, it's got these handles with wheels attached, and that allows you to move it around relatively easy because one person can't really just pick up and move one of these. Some of them have been made to quite large sizes. I think there's some that even have 1 metre diameter mirrors, or maybe even larger. But that's definitely not terribly transportable once you get up to that size. But works in essentially the same way as the simpler Dobsonian we saw before. Okay, this is another kind of Alt-az mount. This one is a computer controlled one. It allows you to, it's actually an Ioptron AZ Pro, I think it's called. And again, it rotates in azimuth, and you have an altitude bearing that you, with a basically a holder for a dovetail connection to your telescope. So the telescope fits on this side. I believe you can optionally have a dovetail on both sides. You can have maybe a telescope on one side and some kind of camera or another telescope on the other, or otherwise to balance you can put on a shaft with counterweights on it to balance out your telescope. You always, in these kind of mounts where the telescope is being held on one side, you'll usually have some kind of balancing issue, um, especially when you get to larger sizes. This is an example of an alt-azimuth with a Schmidt-Cassegrain, and you notice this one is only supported on one side, the declination drive there. Sorry, the not declination, I mean the altitude drive there, and the azimuth drive at the bottom. And because it's not a large telescope, it's not too hard to engineer this without counterweights. You just basically transferring the load into the tripod legs. Here we go with quite a common arrangement, a Schmidt-Cassegrain on a fork mount. And when you think about it, a Dobsonian mount is really just a simplified fork mount, really. Um, but instead of sitting on a tripod or a pier, the Dobsonian just sits on a basically rotating plate. Um, in this case, this does have drive motors again for the altitude up here, and an azimuth drive motor down the bottom, and so it's an Alt-az telescope. Now it turns out any kind of Alt-az mount can really be turned into an equatorial mount, and I'll explain how that works later on. First of all, given that you've got computerized alt-azimuth mounts and they will track and find objects, why would you bother with an equatorial mount, seeing that it's a lot more trouble to go to? So the Alt-az mount always has to drive both axes if it's going to be tracking stars. An equatorial mount can track just in one axis. If it's polar aligned, you just need a sidereal drive on the RA axis, or right ascension axis. So you might, if you ever saw the Zeiss telescope, before it got its big motorized upgrade. It was a push-to telescope. You'd have to move it around the sky, maybe using the visual setting circles, find a scope to find things. But then you would engage the sidereal drive, and after that the telescope would track a star or nebula or whatever you were viewing perfectly fine with a nice sidereal tracking rate. So what is the advantage of the Equatorial? You can obviously do this with a Alt-az mount. You can go to track objects just fine. And the reason is actually to do with photography. And just to explain why, I've got this. It's basically a screenshot of stellarium looking towards the south celestial pole, and we imagine that we've got a telescope on an Alt-az mount with a fairly wide field of view so that it's encompassing the Southern Cross, as you can see there. And we go a bit forward in time, a few hours. Southern Cross is now all the way down here, and our Alt-az telescope has been tracking the Southern Cross, so we've still got this Southern Cross nicely centered. But you'll notice that the Southern Cross is actually rotated in the field of view. Imagine if you had a camera which would, imagine the image on the camera was a nice square like that. The Southern Cross would have rotated almost 90 degrees in this case. So if you were taking a really long exposure of several hours, all you would get would be the stars would end up as circles, or not a complete circle, but part of a circle, a type of star trailing. And you can get this effect if you just, or a related effect, if you have a camera and lens just fixed, not tracking at all. You will see that in that case the stars will appear to rotate about the south celestial pole. You get some quite nice star trail images. But even if you're tracking the stars, you still get rotation inside the field with an Alt-az mount. So an equatorial mount automatically takes care of that, because the polar axis of the equatorial scope, or the right ascension axis, rotates the telescope around the pole, and thus the field of view doesn't rotate. So it means that you can take long exposure um, of the stars or nebula, and you don't get rotation within the field of view. Now, it is possible to dial out that field rotation. In fact, that's what the very large observatories do, like the Keck Observatory, where engineering-wise an Alt-az mount with a scope of that size is the way to go. But to cater for this field rotation problem, they actually, any sensor or camera, they just apply a rotation to the camera that cancels out the field rotation. And a little bit tricky because the field rotation isn't constant, and you really need a computer to do it, and I'll explain that a little bit as well. So here we have it, the angular rate of field rotation. It's actually not that trivial a formula. It's the rate of field rotation there in degrees per hour is a constant k known as the observer's constant, multiplied by the cosine of the azimuth divided by the cosine of the altitude. And the value k is actually the angular rotation of the Earth in degrees per hour, and you multiply that by the cosine of the observer's latitude. And the reason we say that it's an observer's constant, because when you're an observer, you're not going to be changing your latitude. You're going to be observing from one spot at any given time. And that funny value, 15 point blah blah blah, that is effectively the sidereal rotation of the Earth, meaning in the sidereal rotation of the is 360 degrees divided by the number of hours in a sidereal day. So, and in the formula, as I said, the value AZ is just the target that you're tracking is the azimuth angle, and obviously that changes all the time as you're tracking it, and the altitude is the target's altitude angle, which also changes. So the formula does have a little trick in it. If you're dividing by the cosine of the altitude, and at 90 degrees, cosine of 90 degrees is 0, so you get a divide by 0. It's not actually a mistake, and I'll explain a little bit here. First of all, this is basically a chart showing you for a given latitude. I can't remember what the latitude was for this particular chart, but it's showing you the calculated field rotation in degrees per hour going from 0 to 60 down to minus 60. So the rotation can be either way depending on your azimuth. So in this case, the azimuth runs along this axis from 0, which is north, back to 360, which is also north, and showing your altitude running from 0 up to the zenith. And you can see that it's not a simple graph, so this is why if you're going to put a derotator on your camera or whatever equipment you're using, you have to have a computer to compute these numbers and apply the exact rate of rotation that you need depending on where the target is in the sky and where the observatory is. Slightly different chart. This is one showing what the maximum rate of field rotation is for any given latitude. And you'll notice the greatest value for field rotation can occur at the Earth's equator. So as you get down to higher latitudes towards the poles, the maximum rate of field rotation gets less until when you're at either the North Pole or the South Pole, there's no field rotation. So if you put your observatory and telescope at the North or South Pole, have an Alt-az mount, don't need a field derotation, nothing to worry about. Its problem is fixed. You've just got to live at the North or South Pole. And just to explain what's happening with if you had a camera, imagine this is the camera sensor, which is a rectangle like this, and you have a field derotator on. Over the course of the exposure, the field derotator is slowly rotating the camera, and basically with the rotation opposite to the field rotation of the Alt-az mount. And so you end up with your picture with no star trailing. So alternatively, if you have a equatorial mount, you don't have to worry about a field derotator. So what kind of equatorial mounts are there? Well, there's basically a fork mount we saw before, which was basically a Dobsonian as a type of fork mount. The fork mount we saw on the Schmidt-Cassegrain, but we can actually use a thing called a wedge, which basically you sit under the base of the Alt-az mount and you basically tilt it to set. Usually it'll have a scale on it with an adjustment, so you can tilt it to whatever your latitude is. So for example, in Auckland we're about 37 degrees south. You'd tilt the wedge adjustment to 37 degrees. So basically, if you can think of it like this, the entire mount is being tipped over 37 degrees, and what was the azimuth mount is now the polar mount, or the right ascension mount in equatorial terms. Axis is what I meant to say. So there are some specific German equatorial mounts. There's the cross-axis mount. I'm not sure how common those are, but there's a few of them. You've got the German mount, which a lot of amateur telescopes or amateurs will use, and some of the larger professional observatories use a yoke or a horseshoe mount in equatorial mode. So this is an example of a fork mount running in equatorial mode, and you notice down the bottom here the what was, if you imagine it back in alt-az mode, this would have been the azimuth bearing, has now become the polar bearing or the right ascension axis, and this um, block here that is mounted on is providing the necessary tilt for whatever the latitude of this telescope is. But you notice that there is an engineering issue with this. You've got this is quite a large scope, and there's quite a torque being applied to this axis here, or the bearing here. So basically, the bearing has got to be built strong enough to transfer that to the base here without binding up the bearing. So how do you do that if you've got a really large telescope? One thing you could do is this, where you support either end of the RA axis. This is called a cross-axis telescope. You still have a counterweight to counter the weight of the telescope itself. And you notice there's a declination setting circle there for adjusting the north-south rotation. This is a fairly high-endish amateur German equatorial telescope. I think this one is an astrophysics brand one, and you can see these adjustment knobs here allow you to adjust the altitude. So you set that to whatever your latitude is, so that effectively the mount, that the counterweight, you notice the axis, the counterweight on that's basically pointed at the local celestial pole, northern hemisphere, south celestial pole, southern hemisphere at the south celestial pole. Can't quite see it here, but there's a couple of knobs around this side, and they allow you to adjust the azimuth of the telescope, of the mount rather. So you basically have to have the mount aligned so that it's pointing north-south. So as well as this angle up here is pointing at the angle of the pole, the line through here has also got to correspond to the line of your local meridian. It's got to be lined up with the true north-south line, if you can imagine that running along the ground. So it's hard to get that exact just by positioning the mount. So you have little adjustments knobs there to move it maybe for a few degrees either way. Similar but smaller kind of mount. This one, instead of on a pier like the other one, is on a tripod, and you can see again there's the azimuth adjustment knobs, and you've got your altitude adjustment. So you adjust the tilt of the whole mount to set it to whatever your latitude is. This is the Zeiss telescope. Many of you would have seen this. This was during the, I think it was when the telescope was being put back on, when it was first reassembled after the automation, where various drive motors and encoders and whatnot were installed, so that it's now completely computer controlled. This is also a German Equatorial, but it's slightly different. It's called an offset Equatorial. What do we mean by that? Well, if you've noticed, the pier comes up from the floor, and then there's a bend in it that goes up to the RA axis here, or the RA bearing, and that bend is customized in the factory for the latitude of the observatory. You can make fine adjustments to it underneath the floor of the observatory. There's a big shoe where you can adjust both the azimuth and the altitude to make fine adjustments. but essentially it was manufactured for the latitude that the telescope has. So if you move this telescope away from Auckland and there wasn't enough adjustment in the base, you would have to rebuild the pier or use a new pier. The reason it's the purpose of the offset, rather than the mount sort of being physically directly above the pier, it's offset towards the south of the pier, and that allows the telescope to swing under the mount. Those other German equatorial mounts, you can't do that because the telescope or cameras or whatever would run into the pier. So those ones you have to go over the top of the mount. The advantage of coming under the mount is that it keeps the eyepiece at a reasonable height on a large telescope like this, or cameras and other things. Um, so that's a German equatorial with a pier offset. Okay, just quickly look at a couple of others used with large telescopes. This type is called a yoke mount, where the RA axis is again supported at both ends, as well as the deck axis being supported on either side. So thus solves a lot of mechanical issues. The problem is that you have to have more supports than you would for an Alt-az. And the other downside is you can't get all the way to the north or even close to the north, because the telescope actually runs into the mount. Fairly famous telescope, the 5 metre Mount Palomar telescope, solved this problem with a horseshoe arrangement. So north is that way. You can see that the telescope, if you want to point it quite a long way north, goes inside the horseshoe, so you can look quite a long way north without crashing into the mount. Equatorial mounts have an issue. You can't really deal with due north so readily. It's comes a bit of a problem. If you think of an alt-azimuth pointing at the zenith, in theory you get a problem at that point called gimbal lock. Okay, with equatorial mounts, balance is a big issue, and especially with a German equatorial or any kind of mount where the telescope is being supported just from one side. So, as is the case with the German equatorial, there are a lot of other types of equatorial mounts. You can look them up. There's the English mount. Won't worry about it too much. Don't see too many amateurs using them these days. So what do we have to do? We've got the issue with the telescope is usually held by what are called tube rings. So what you do is you can move the telescope up and down in the tube rings, which balances it on the declination axis. And if you put a heavy camera on the end, you might want to move the telescope further up in the tube rings to keep it balanced. The basic idea is you don't want to put too much unbalanced load onto the gears. Usually you'd put a small amount of load just to make the gears engage, but you want the fairly good balance. And again, on the RA axis is a bit more of a problem, because that is you have to have some way of counterbalancing the whole weight of the telescope, camera, and any finder scopes or guide scopes, any other gear you've got on there. So you do that with an extension to the shaft on the opposite side to where the telescope is, and with counterweights normally, and you can adjust the number or size and the position of the counterweights to balance on the RA axis. And again, you don't want to overload the RA axis, so you want reasonably balanced, but again, just with a little bit of weight there to engage the gears, so you take any slop in the gears away. Just explaining what's going on with an equatorial telescope. In this diagram, it shows you the Earth scaled down in size somewhat, or you could think of the telescope scaled up to a really large size. The Earth is rotating around its polar axes, north and south. So what we're trying to do is get the polar axis of the telescope, or the RA axis, perfectly aligned with the rotation axis of the Earth. And so you can see here that the tilt of the mount is just equal to the latitude, and we have the altitude, sorry, the azimuth adjustment of the mount is going to be just basically pointed to the north-south line between the horizon north and south. So this is the northern hemisphere example. In the southern hemisphere we do the same thing, but the alignment axis will be pointing down to the South Pole. And by doing that, we've basically automatically dialed out the field rotation problem I was talking about before. So polar alignment is actually not all that straightforward to do it really accurately. The first thing that's recommended is to level the mount. Now, strictly speaking, you don't have to have it perfectly level, but the more level it is, it makes the remaining steps simpler. So to set the mount altitude, you look up your long latitude on a map. That'll tell you what it is at your location, or you can use a phone with a GPS receiver. Will tell you to much higher accuracy than you need at this stage. You set your mount altitude. You might have a scale. It may not be that accurate. You could use something like a protractor, but again, you're not going to get super accurate at this point. This is just to get a rough alignment. And again, you set the azimuth. Now you can, there's a few ways you can do this. You can use a magnetic compass, but you have to adjust for your local magnetic declination, which you can look up. Some cell phone apps with a compass app will have the magnetic declination map built in, so it knows where you're located from the GPS, so it knows what the magnetic offset is. And I've found a number of different phones, they can vary quite a bit, so I wouldn't rely on them too much. Some of them do quite well and others not so well. Given it's just a rough alignment at night, you can look at the Southern Cross and the pointers. Use that method if you know it, of running the line down the long axis of the Southern Cross, and the line bisecting the pointers where they cross is roughly the South Celestial Pole. You can use that to line up the azimuth of your mount. You can also use the star Achernar. If you run the line between Achernar and the Southern Cross, the halfway point is roughly the South Celestial Pole. If your mount is in a fixed position, you can determine your north-south meridian line using a plumb bob shadow. So you have to do this at your local solar noon. You can look this up on dateandtime.com. You give it your location and the time of day of solar noon will be given, and then you look that up on a clock. I think at the moment solar noon is a little bit after 1 p.m. So daylight saving has an effect, but also the equation of time. So you can't just use simple noon clock time or clock time based on daylight saving time less an hour. That won't work, because it depends on exactly where you are. You're going to be offset from the standard meridian depending on where you're actually located. So yeah, dateandtime.com is a good source for that information. So when it might say that solar noon is at 6 minutes past 1, so you mark your shadow line, mark it on the ground. That gives you your north-south line and lets you line up your mount during the day. One thing is you've now got approximate solar alignment. It's probably good enough maybe for visual use, but not for photography. You have to get it quite accurate to be able to do photography without star trailing, both just because of the drift and the position. So you can get a lot of equatorial mounts will have basically a hole up the middle of the right ascension axis, and you can, some of them come with it, some it's an optional extra. You fit a polar alignment scope. Problem we have in the southern hemisphere that you have to be able to see some quite faint stars. The nearest Brighton, I put Brighton in quotation marks because Sigma Octantis is about magnitude 5.8 or something like that. So practically a sixth magnitude star. It's really, really difficult to see, especially from the city. It's probably impossible, even in one of these alignment scopes. You probably, unless you've had a lot of practice, you're going to have trouble. Probably from a rural setting, with a bit of practice, you can do it. What the polar alignment scope has it in it is an illuminated reticle, and it basically you can spot Sigma Octantis and some other stars, and you position, make your altitude and azimuth adjustments to position those stars on the marks in the reticle, and then once you've done that, you'll have quite good polar alignment. Um, there's better ways depending on what equipment you've got. So, this is just showing you what a reticle might look like. So Sigma Octantis there is about 1 degree from the south celestial pole. So if you position if you can see these stars under the reticle marked like that, um, then you should be able to get reasonably accurate polar alignment. Um, but the problem, as I said, is actually seeing these stars, especially in the city. It's actually quite difficult. In the northern hemisphere, they're a bit lucky. They've got a relatively bright star, Polaris. Um, just to show what the field looks like, an image to the same scale as that reticle I showed there. But the trouble is, if you look at it through the polar scope, the stars are going to be much fainter than you see here, even in the scope. The polar scope has quite a small aperture. Again, that one there is Sigma Octantis. So we've got some other solutions. Traditionally, the way to do it was called drift alignment, and this can be arbitrarily accurate depending on how careful you want to be about it. Um, I've said it's the most accurate, probably. There are some other photographic methods that are probably just as accurate these days, because they're effectively using a form of drift alignment. So um, you can get software that can help with these things if you've got a camera. But if you're just doing it visually, I'll just run over how this is done. It says it's scary, it's tedious, and it requires practice. Maybe it's worth doing it at least once just to understand how it works. And probably if you've got a permanent observatory, definitely probably worth doing this. You have to be careful that your rough alignment is pretty good to start with. I know out at the QMU Observatory, when they put the new mount or the refurbished mountain telescope on there, it was a bit of a trap because there was a mark on the base plate that the mount sits on, and the assumption was made that that was marking the north-south meridian, but it turned out it wasn't, and so that made things really, really difficult. Eventually, they figured out what was going on and used the plumb bob method to find the correct north-south line, and then they were able to use a drift alignment procedure to correctly align, with the help of a camera as well. But I'm going to go over how to do it visually. Just to say that the Zeiss telescope at the Stardome, the drift alignment of that was done back in 1967, I think. It's never had to be adjusted since, and it tracks really well. The only thing that can really mess it up is probably plate tectonics, like if an earthquake rotated the land the observatory was on, or it significantly moved north or south. So eventually that will happen, but so far it's still tracking fine. That was over 50 years ago. Okay, the general procedure. Now this is where levelling the mount is helpful, because if you don't level the mount, then these two are going to affect each other. So if the mount is truly level, then these two adjustments are going to be independent of each other. In reality, you're never going to get perfect levelling, but if it's close to level, it'll minimise the interdependence of the two adjustments. So we've started off with a nice level mount. So the first thing we want to do is correct the azimuth. So there will be an error in the azimuth pointing of the mount. May not be aimed truly south, it might be a bit off. So we fix that first until there's no detectable north-south drift. And I'll explain that a bit further. So you then correct the altitude error, and to do that, oh sorry, I didn't explain one thing with the azimuth. You pick a star that's near the meridian, so either recently crossed or about to cross the meridian, fairly close. You don't want it on the meridian, because that can cause a problem for some equatorial mounts won't go very far over the meridian, so you don't want a meridian flip to have to occur while you're doing this, but maybe within an hour either side of the meridian. And you want the star also to be near the celestial equator for best use. So you use that star to dial out the north-south drift while you're observing it. You then swap to a star that's lower down near to either the eastern horizon, maybe up about 20 degrees, or you can use the western horizon as well. Again, you dial out the altitude error this time, and you keep repeating and repeating and repeating until you cannot see over any drift at all over whatever time limit you like, 5, 10 minutes, or maybe even longer if you're really keen. Okay. I'm not sure that I got this quite right. It doesn't matter anyway. Um, I think I might have this the wrong way round. I might have copied the northern hemisphere stuff by mistake. But basically, the star near the meridian, you need to align up a reticle eyepiece so that east-west motion is along one line of reticle, and the north-south is along the other. I'll show you what that looks like in the next slide or two. Basically, if the star near the meridian is drifting to the north, it tells you what the error, and I think it should actually say that the telescope should be rotated further west if it's drifting north. I'll have to think about that. It doesn't matter too much, because if you make an adjustment and it makes it worse, then you know you went the wrong way. So you just keep making an adjustment till it gets better and the drift gets less. And basically you do the same thing with your star closer to the horizon. Again, you don't care about east-west drift in either of these. it's only north-south drift that you're interested in, and you keep dialing it out using the meridian star, dial it out using the nearer to horizon star, using the altitude adjustments. So you go meridian star, adjust the azimuth, star nearer to the horizon, adjust the altitude, and it's basically a repetitive process until there's no more drift. So this is the sort of reticle eyepiece you need with an illuminated reticle. You'd position your target star in the middle there, and you'll line these lines up so that was your north-south drift line, and that's the east-west line. The way you figure out the east-west line is you turn your drive off, and of course the star is going to drift east and west, so that's how you do it. Turn your drive off, watch what the star does. You turn the reticle until the star is drifting along right in the middle of this line and staying in there, and that means that part, those lines in the reticle, are lined up with the east-west. So that's how you set the reticle up before you start. And it's just showing an example here with a star, and so the star is going to drift along that way if the mount is turned off. And this is kind of showing the sort of thing that happens. This is the meridian adjustment. If the star drifts up, then you've got to make an adjustment to the azimuth that way. If it drifts down, make the adjustment that way. This depends on the type of telescope, because depending on whether there's diagonals and things like that, so it can be a bit confusing. Probably the easiest way to figure it, that you're going the right way, is if you make a small adjustment. If it gets worse, you're going the wrong way. And this is what it looks like on the star near the horizon. So this time we're making the adjustment in altitude. So and the drift again will either be north or south. If you can imagine things um, in sort of like spherical geometry, and draw the lines parallel to your axes or the great circles, and think about misaligning them, think about what happens to the star if the alignments are out. That might help you to understand what's going on here, but it's easy to get really confused. But yeah, if you just make the adjustment so that you adjust in the direction where it's getting better until it's not drifting, and then swap to the other star, keep swapping backwards and forwards, and eventually you'll see there's no drift at all. So you can get these fancy polar scopes that have a built-in camera that you connect up to a computer with software that basically tells you what to do it, you know, to make these adjustments. Probably makes it a little bit easier. There's QHY make one called the Pole Master. There are other ones. You can just use a guide scope with a webcam or planetary camera and the SharpCap software. And there are various other ways you can do this with the aid of a computer. So that's the end of the presentation. As I said, if you have any questions, we'll have to answer them via the chat, because I've pre-recorded this session. Hopefully it will shed some light on the different types of mounts, and thanks a lot. Sean will be here next week to do a talk on an astrophotography subject. Thanks everybody for listening in.